Okay, today we're going to be talking about the soil geochemistry results that we've had returned so far from Crunchy Hill. Crunchy Hill is one of the Latori targets from our Kuriku Lost Cities project in southeastern Ecuador. I was there several weeks ago and I picked up this rock. Doesn't look like much, it looks like a piece of slag. And the reason it looks like slag is because it's composed of iron and it's full of holes, just like a piece of slag would be. The reason we call Crunchy Hill is because when you step on this stuff, it's very porous, it collapses out from under you, and it crunches underfoot. So hence the crunchiness. The reason that this is composed of iron is because originally that iron would have been caught up in iron sulfides like pyrites, and they've all weathered away to a combination of things called goethite and probably some hematite. These are iron oxides. So that's part of what Crunchy Hill looks like. And also at Crunchy Hill we have banded epithermal veins, and you can see the banding right here, and these occur at all different scales right down to the millimeter level. And so in some cases the rock is completely riddled with these crisscrossing veinlets, and the supporting rock is actually weathered away completely, so that it's just left more or less a lattice work of quartz behind. Anyway, so we've been taking samples of soil anywhere from 30 centimeters to 60 centimeters down into what's called the B horizon soil, and analyzing that both with our portable instrument and then later on in the laboratory for various chemical elements. And this is the pattern that we see, very, very similar to what we get in the stream sediments. And of course, in the stream sediments, what we're looking for are elements that statistically we would say co-vary together. So these are elements that are co-enriched, so they occur in the same places. And when you get this sort of a development in the data, it really does support the idea, the thesis, that there's going to be something that's generating these targets, which is at depth. So we're not necessarily looking for gold on the surface. In fact, we think this kind of target doesn't lend itself to having gold on the surface because we're finding enrichments in what are called the volatile elements on the surface. Volatile elements are things that end up in fumaroles, in gases, in hot waters, geysers, mud pools, things like this in a geothermal system. Think things like Yellowstone and Old Faithful. So in that kind of an environment, you have a lot of arsenic, you have a lot of antimony, and the sort of elements that we have right here, which are showing up in the gases and in the vapor that's coming up to the surface. But down below that, at say 100 meters, 200 meters, 300 meters depth, where the fluids are actually boiling, that's where you're going to get the gold and silver, and it precipitates out of the fluids. So what happens when the fluid boils? The chemical complexes that are carrying things like gold get destabilized, the gold drops out of solution, and it ends up in the veins. So this is a very, very pleasing result for us. So what I have along the top here, I've got 5 different elements that co-vary together. They have almost exactly the same pattern in the geochemistry. We laid out a grid on the surface. The grid, for the most part, the lines are 100 meters apart. And then along the lines at the sample sites, we call them stations. The stations are more or less 25 meters apart along the lines. And we take the samples in each place, and then we plot the results on the grid and on a paper map. So what we have across the top here, we have 5 different elements that seem to co-vary together, meaning that the patterns are very tight, and we're getting enrichments of the same elements in the same places. So the data supports each other. It's really, really interesting. So this is moly, silver, molybdenum rather, silver, mercury, antimony, and arsenic. And then underneath it, we have thallium, manganese, zinc, and selenium. Now, selenium and thallium are co-enriched also in the same sort of places as the ones along the top. For manganese and zinc, we're getting more of a dispersion. Manganese is getting exceptionally high, up to 21,000 parts per million. That's over 2% in the soil. That's very, very rich, and that's telling us that there are actually manganese minerals that are generating this kind of an anomaly, probably things like rhodochrosite. That's exciting because rhodochrosite is a manganese carbonate, which is very, very common in Fruta del Norte, about 100 kilometers to the south, the big gold deposit. So what we've got here, it's kind of a techno modern day treasure map, if you wish. So using technology and using geochemistry, it's more or less X marks the spot. So where would you drill on this? You would drill right to intersect underneath the target. So the chances are excellent that the mineralization that's causing these patterns is sitting directly underneath this. So the next steps in this exploration, we're going to do some trenches across the soil anomaly to see what's in the subsurface, down maybe 3-4 feet. And also we'll do something called an induced polarization, an IP survey. That's a geophysical survey to detect sulfides at depth. So that'll be a very, very interesting result. That's coming up soon. So in our last press release, we said that we have traced Crunchy Hill now for 1,000 meters from the original outcropping zone. The original outcropping zone is in here. Now you get a sense from the soil data that there's something over here. And so what we've done in the last couple of days, we haven't got the results back yet, but we've extended this grid out to the west because 1,000 meters from here, we're getting the same sort of crunchy looking rock, and we expect that it's going to be enriched in the same sort of elements. You get a bit of a sense of it here, but certainly it continues off to the west, and that's very exciting.